Thank you. And in this brief presentation, I'm showing you and illustrating you the two models that we proposed in the frame of our project. But before start speaking in detail about the two models, I just want to introduce them as a part of a broader family of the input-output framework. And I hope and I'm sure that many of you knows about the input-output analysis framework that actually is grounded on empirical, economic, or physical input-output tables. And here's just one example of the mathematical algebraic structure of those tables. Actually, these are collections of empirical, economic, or physical flows that are exchanged across regions and sectors within regions. So this table represents, as an example, the intermediate demand and supply of products across regions. You see Russia, EU, and rest of the world as just an example. And of course, the light red blocks, the international trades. Then the final demand block that collects the demand of households, government, and investments by each country, and of course also the trades of products across regions, and then the so-called environmental transactions. These data are provided by economic bureaus of many regions, and also are provided in the form of multi-regional tables mapping all the structure of world economic activity in a standardized way. And these tables are available and are the ground and the underlying data for building input-output models. And what are input-output models? Essentially, these models are starting from the empirical data that I have introduced in the previous slides, by defining the so-called technology matrix, so the technical coefficients that are characterized how each technology within each region is demanding for inputs of products coming from other sectors and other regions in order to provide one unit of its output. So this is basically the essential data that is required to build and to provide the Leontief production function that then could be used in an algebraic system of equation in order to derive what would be the output, the total output of each activity in each region, given a set of technology represented by the technical coefficient matrices that are likely to be produced if a given level of final demand is demanded by final demand agents. And of course, once this total production or total activity by each sector in each region is defined, then it is possible also to derive the exogenous or environmental transactions in terms of, for example, CO2 emissions, water use, land use, and other environmental transactions within the nature and the economy. So this is a general framework in its simplest shape, and based on this framework, then this can be elaborated and further elaborated and be transformed based on a linear programming model and enriched with other equations and side constraints in order to represent a greater complexity in production system. And to provide and to deliver final models that are specifically devoted to the analysis of peculiar problems. Now, the major world multi-regional data sets that are available are provided by agencies like OECD, of course, or are the results of EU-funded projects like the ExioBase project. For example, and each database provides a granulometry or disaggregation of sectors, regions, and products that, of course, is variable. And this just to say that depending on the research question that we have, we can select a database that is more suited to reply to this question. For example, we are relying on the ExioBase database if our objective is to provide an in-depth reply to some key questions from the technology point of view, since it has a regional coverage that is not so high, but it has a high level of disaggregation of sectors. Okay, so once a database is defined, depending on the question, the research question that that we need to address, then of course the input-output model can be enriched and can be transformed to be more complex than the simple algebraic form that I showed you in the previous slide, in order to represent some complex phenomena in the real world that we want to address. And one thing to say is that we have developed the Mario Python package that stands for multifunctional analysis of region through input output, that essentially is a database handler. So we recognize that handling an input output data set, implying handling huge input output tables that may collect a lot of numbers that need to be handled in order to deliver detailed models that can be used for scenario analysis. And the Mario Python package allows to handle such database in order to rearrange regional and sectoral structure, in order to model the addition and inclusion of new industrial activities or new commodities, to assess the impact of such industries and commodities, and then to perform various types of impact assessments. So handling numerical perturbation in order to assess, for example, what would be the impact on the overall, I don't know, CO2 consumption if a shock in the industrial production, so a structural change in industrial production of a region is exogenously imposed. Then, based on word input-output data sets that are handled by the Mario package, we can provide the suited empirical data set that is needed in order to deliver models. And speaking about models, then we of course have developed many different type of models that fit different purposes, but for the purpose of the project, we believe that the world trade model with bilateral trade and the dynamic extraction and recycling input-output models are the one that are, let's say, useful in order to, or that are fit the research question of the work package we are involved in. One mention important is that we can use input-output tables also to provide some small conceptual models for teaching purposes and we believe that, and we proved that in the past, using input-output tables in order to provide a simplified sketch of economic systems is very useful for teaching and for capacity building purposes. Speaking about detailed models, let's start from world trade model with bilateral trades. I will be very brief because I provided a very broad introduction on the framework. Basically, the world trade model with bilateral trade is an elaboration, a development of a standard input-output model that is nothing but a optimization model that works as with a comparative advantage principle. So it is a meso-economic linear optimization models that is specifically devoted to the analysis of bilateral trades, international trades of goods and services across regions and sectors, that is defining the least cost trade pathways across regions based on the minimization of factor use. So once a data set is defined, so an input-output database that is depicting or taking a snapshot of an economy in a given time frame, then setting up a world trade model will lead you to a scenario that is minimizing the cost of factors, so to an optimal arrangement of international trades that should resemble reality if constraints are properly added. And then by further constraining the model, like, for example, adding some constraints on CO2 emissions based on by simulating some sort of policies like carbon taxes, for example, then the model is returning a new arrangement of international trades in a comparative statics way by returning a new arrangement of international trades that leads to a new arrangement, of course, of a new set of emissions, of course, due by all the sectors and all the regions. Then, of course, also other type of policies can be tested, like, for example, some exogenous change in the mix of technologies for energy production, for example, or some other technology mix for or technology or testing some effects of structural changes in some industry production technology in order to see what is likely to happen to international trades based on the minimization of factor use. Here, just an example to put this on the ground. We tested the application. We made a comparative test applying carbon taxation mechanisms based on a production-based or a territorial approach. So the standard way carbon taxes are applied, and you can in the U27 in the scope of the Europe. And then we see that by applying a carbon taxation, something very trivial occurs. So while the production of products was shipped outside country border, so outside U27, by increasing emissions outside Europe, so the famous carbon leakage phenomena occurred. While if you apply carbon taxation mechanism based on a consumption-based accounting, so you practically constrain the emission embedded in final demand instead of constraining the direct emission of products, then something opposite occurs. So the emission, overall global emission, decreases because the model was forced not just to find the arrangement of international trades that minimize the emission of Europe, but more efficient arrangement of international trade that minimize the overall emission of CO2 worldwide. This is just an example of the possible application of this kind of model. So this is focused on international trade analysis and can investigate the bottlenecks in terms of industrial production capacity or resource availability in the global supply chain system. Or, for example, as I said, can investigate the impact of emission in the change of production mix, and, for example, in testing what would be the effect if some change in final demand occur in future years. These are kind of broad questions that this model may be able to reply to. In terms of SDGs, of course, this is a broad model because it encompasses the whole economic system. So it may, of course, be useful for investigating the SDG 8, 12, or 13, so climate action, responsible consumption, production pathways, and then decent work and economic growth. And there are a bunch of publications that can be looked at for digging into this modeling framework.